Good evening, and thank you for joining us for this live-streamed presentation hosted by PEEC, also known as the Pajarito Environmental Education Center. I am Joyce Guzik, and I will be the moderator for tonight's talk. And tonight's talk is being recorded. And as you see, the title is A Short History of Astronomy with Jeremy Best. So PEEC is able to offer programming at this time because of our wonderful members and donors. And we will send an evaluation form to you after the talk, and we'll use your comments and your suggestions to improve and create future programs. So I hope you will fill that out. So now I'd like to introduce Jeremy. Jeremy is an amateur astronomer, an astrophotographer, and a volunteer with the Pajarito Astronomers. He's our secretary and treasurer in that club, and he's also does many other community volunteer efforts. Jeremy is also a retired Marine officer and current program manager at Los Alamos National Laboratory. Jeremy has a very supportive wife in all of these activities, Jennifer, and two very enthusiastic children, Alexander and Adeline. And I am really surprised at this, but with all of that going on, Jeremy also finds time to volunteer as the president of the Barranca Mesa Pool Association. He is a French horn player and performs with the Los Alamos Community Winds. And he is also a mentor for the Horses for Heroes program in Santa Fe. So I'd like to now invite you to listen to Jeremy's talk on a short history of astronomy.
Thank you, Joyce. Very, very nice introduction. As she said, we're gonna do a short history of astronomy. And it is a short history because the actual history of astronomy could take up several classes in an undergraduate education sequence. And it could also take up several hours of me droning on. And I don't think any of us really want that. So we're going to start as far back as we have dated records. And that's actually pretty far back, farther than 1000 BC, where we have actual archaeological evidence of people looking up at the sky. Now, I mean, if you can imagine a sky devoid of lights, terrestrial lights as we see them today in cities, and just being able to have true dark skies everywhere you go, and just see the amazing sights of the heavens beckoning overhead every time the sun sets. This was one of those things that I typically think about whenever I stare at the night sky now, and we have very good skies here in Los Alamos, but just trying to imagine a truly dark sky with no artificial lights, it still kind of boggles my mind a little bit. But whenever the early man started getting through the life-threatening issues of just basic survival, they did start to try to understand what they saw in the sky. And, you know, they started making paintings and drawings. And even the piece to the left is a piece of bronze that has the moon in various conditions, and also a cluster that has been identified as what we know today as the Pleiades star cluster, the Seven Sisters. So as far back as we can possibly look, we have evidence of mankind looking to the sky and really trying to understand what they see. And that leads right into a combination of Eastern and Western philosophies. So the philosophy and astronomy, especially early on, go hand in hand. The Chinese have records from their very earliest recorded history, and on the right is a depiction from very, very early on of different comets and their tails. So those lines that you see and the different drawing types are different comets of different times of the year and how they looked visually. So this is recorded, I believe, I can't quite remember. I believe it was on something akin to parchment or something that would last a very long time. It was on a scroll, as I recall. And then we go into the more Western school of thought. And a lot of people think that the Greeks and Romans started the study of astronomy, but it actually goes back a bit farther than that. And the Babylonians really started the first scientific astronomy recordings around 700 BC. They were really keen on trying to understand the movement of the stars, the movement of these bodies that they didn't quite understand. And that leads us into a great debate that started. But to dispel the myth that the Greeks and the Romans started this, it was really the Babylonians. The Greeks and Romans inherited a lot of these studies, a lot of the scrolls, a lot of the writings, and the verbal teachings that came down. They were inherited as the Greeks and Romans civilization really started getting going. And so they kind of had a head start, if you will. And then the Greeks specifically started developing theories or ideas on how all of this works. What do we see in the night sky? Why do things move the way they move? And how do we record them? How do we get accurate recordings to try to understand the nature of these? Because they started understanding a little bit more about the seasons and how certain star clusters or certain what we know as planets now, how they would move across the sky at during different seasons. So that led to a lot of theory and ideas about how this all works. And the first early theory was somewhat natural if you think about it. If you're standing on Earth and you see everything around you, you can assume that where you're at is the center, because as you look up at the night sky and even the sun and the moon, they appear to rotate, and they are very periodic. They have a regular nature to them. So the early observations, the visual observations, sparked a great debate on what is the center of the universe? What is the center of what we see? And there were quite a few philosophers, specifically early Greek philosophers around 300 BC, who were trying to figure this out. And they came up with an idea that the Earth was the center of the universe. The Earth was the center of all that is, because that's what they could see. And the early philosophers were Plato and Eratosthenes, who came up with this idea that the Earth has to be the center because everything appears to rotate around the Earth. Now, Eratosthenes was very unique in that he started using math to determine distance to these celestial bodies. Specifically, he looked at the sun and the sun's rays and trying to understand how far away is the sun if we use mathematics. And keep in mind that math was a very early thing at this point. It wasn't as well developed as we know it today. So the distance from Alexandria to Seen was determined using the approximate radius of the Earth and some angles and looking at the distances of the sun and how the sun changes over time between these two cities. And it was determined that it was 4,900 stadia. And so the stadia was just about 0.16 kilometers. So then you try to figure out what is the size of the Earth, the circumference of the Earth, and that helps to understand how this math comes in with the sun's rays shining down on the Earth. It was really quite unique whenever they figured this out, specifically Eratosthenes. And so then there became a debate because Aristarchus, who was another Greek philosopher, came up with this idea that, wait a minute, maybe the Earth is not the center of the universe. Maybe the center of the universe could be the sun. So Aristarchus of Samos came up with the first known heliocentric model of the solar system. And he plotted all of this out, saying that the moon had to rotate around the Earth, and that the Earth was possibly rotating around the sun, which is a very interesting philosophy. And it went against the most commonly accepted model of the universe, which was the geocentric or the Earth-centered model. So if you think about this, these are people, very intelligent, educated people, philosophers of early Greece, who were observing the night sky and trying to make sense of what they saw. And now there's two different ideas, two different thoughts of, is the Earth the center of the universe? It would seem so, because we're standing on Earth and you see everything moving around us. And then here comes Aristarchus, who says, wait a minute, we're moving around the sun. So this created a great debate. And all of the observations, calculations, everything was built up on previous theories. I told you a lot of this came from the Babylonian times, and it was just built up, and there were libraries that were dedicated to housing the thoughts and ideas of all of these philosophers to try to figure out, how does this all work? Up to Hipparchus and then Ptolemy, or Claudius Ptolemaeus. So Claudius Ptolemaeus created what he called the Almagest of Claudius Ptolemaeus. And it was a recorded theory of all of the science that had gone before him. This was about 200 AD, or what is also known as 200 CE, which stands for current era. And he described an off-center Earth with the celestial bodies moving in what we call epicycles, which I have a graphic coming up. The epicycles are circles within circles, and they describe non-uniform motion. And I told you there was a great debate between the geocentric and the heliocentric idea. Well, everyone sort of agreed, based on what they could see, that the Earth had to be the center. So the theory of this off-center Earth moving with everything else moving around it tended to dominate all of astronomy for over 1,400 years, 1,400 years. That's a very, very, very long time. Now, here is a graphic that I absolutely love. And this describes the different ideas between geocentrism on the right and heliocentrism on the left. Heliocentric being the sun is the center of our universe, where geocentric says that the Earth is the center with the sun rotating around us, but everything else moves in these epicycles. And if you watch it, it almost looks like a spirograph. So a little wheel within a wheel that can spin and create interesting patterns. So this is where I like to mention that there is a phenomenon called retrograde, when the planets appear to move backwards in their orbits. And that has to do with where we are relative to the sun and relative to the other planets. But in the geocentric model, these retrograde periods were described by these epicycles whenever the planets would appear to go backwards on their orbits. And so that's kind of how they came up with the idea of planets in retrograde and what it would actually do and mean. So keep in mind, geocentrism dominated for 1400 years. And along those lines, so this is right after Ptolemy, so there was Hypatia of Alexandria, and there's not very many well-known women astronomers, and she is one of the earliest that's recorded, and she was absolutely pivotal to understanding how Greek scientific knowledge could be propagated and continued. Her father was Theon of Alexandria. He was a very well-known, very well-respected philosopher and mathematician, and they lived in Alexandria. She was born in about 355. All of these dates are sort of about, because we don't really know. And she grew up learning from her father, because her father agreed to teach her when it wasn't really popular for women to be philosophers and mathematicians, but she showed interest and her father taught her. So she became the leading mathematician and astronomer of her time, because back in the early Greek days, they were sort of not really one and the same, but they were almost considered the same thing. Mathematics and astronomy and all the sciences were kind of grouped together in this idea of philosophy, how the world works. Philosophy means the love of knowledge. So it's just one of those things that Hypatia never really got fully recognized for the contributions that she made. She taught mathematics. She would be known in modern days as a professor, very well respected actually. And she was respected in most groups, but there were turbulent times. It wasn't all perfect in Alexandria. The rise of Christianity, the church really, really believed that that what Hypatia was explaining about how the world worked constituted heresy, because she was trying to use scientific methods to understand how the world works, where there were a group of Christian zealots who, if you didn't believe as they did, they didn't like you. So she was murdered for heresy by those zealots. And then they went and they found as much of her work as they could and burned it, because she was considered a heretic. And that's not the happy ending that we would like to see. But it did, some of her work was left over and was found later and preserved. Thankfully to any historians out there, historians are crucial to preserving the knowledge that we have. And that's one of those things that I like to mention, is historians ultimately saved whatever work that we could find of Hypatia of Alexandria. And then we jump forward quite a bit into past that 1400 year time period, whenever we start to get into the Renaissance period, the Renaissance astronomy, and sort of the birth of the modern age of astronomy, the fall of the Roman Empire. And there was a fire in the Library of Alexandria, which was one of the most respected and well-kept libraries in the world at the time, or at least the Western world. And there was a great fire in there, and they lost a whole lot of the records, the scientific data, the knowledge of those early times that kind of set a lot of us way, way back in scientific space, because now we didn't have all of that work that went on during the more classical period, the Babylonian, the Greek, the Roman, all of those types of things. So along comes Nicholas Copernicus in 1520, who was truly a trailblazer. He was the first well-known modern astronomer, and he challenged at his own peril to the accepted doctrine of the church at the time. He challenged the geocentric model, and he put forth the heliocentric model, and he really started stirring things up, because until this time, the geocentric model was fully accepted. Everybody believed that the Earth was the center of the universe, and everything moved around the Earth. And then we move forward about 60 years to Tycho Brahe, who was a Danish nobleman. He built an observatory. Now, this is not an observatory as we know today. This was a very rudimentary observatory, and they were using navigation instruments like sextants and things to measure the movement of the stars to figure out time and date and other things. So he created an observatory in the same spot so that he could start having people over, he could do it himself, and recording. Scientifically, once again, we're starting to record the movements of the sky. Now, there's a lot of time period that I'm skipping over, which is why this is a short history, but I'm trying to hit the highlights here. So Copernicus challenged the geocentric model, and Tycho started really observing and having folks come in and observe the night sky and make measurements and record them, which was a huge, huge step in the right direction for our modern astronomical observations. Then we get to the development of glass and mirrors. So if you've ever seen a really old church or a really old building, particularly in Europe, a lot of the glass that you see, if it's a really old glass, appears to have sagged, and it drips over time, because glass is not actually a solid. It is a superfluid. So over a very, very, very long period of time, it tends to run, if you will. So just like water would, but at a much, much slower rate. So the early glass of the time was full of impurities. It was not very clear. It was not the glass that you see today. It was very dirty. It was very bubbly. It was very hard to control the glassmaking process. And only the rich, the very rich, could afford to design or build instruments that they could use to look through. And this is up on top. The green image here is the earliest known illustration. Now, this is just a drawing, but Giovanni Battista della Porta included this sketch. So he wrote a letter in August of 1609. So this is, still very early on in the astronomical observation space, but he drew this up and basically indicated that he could make something to see far objects with. And then lenses were starting to be developed. They still had bubbles. They still had a green hue because there was a lot of iron in the glass. So glass is, think of melted sand and those bubbles. And if you have a lot of iron in it, it tends to make it green glass. And so it's very hard to make good measurements of the night sky when you have impure glass. And they started refining this process over time. And in the middle here, you see the Galileo Refracting Telescope. Now, this has a converging lens on the left-hand side. And then you have a diverging lens, which is the concave part. So and you separate those based on the focal length and some other things. And that gives you a way to magnify what you're seeing by bending the light rays towards your eyeballs. And, it's kind of sensitive to your, what we call the focal plane, but that was one of the early refracting telescopes. And then we have Kepler, who came up with the similar but very different idea, where he used two converging lenses, two sort of oval-shaped lenses, one on the front end, one on the back end. And what that does is that tends to basically flip the image upside down, so you're actually seeing inverted. But it was a little bit easier, I think, possibly, to make these types of lenses. But there were different designs, and they went anywhere from 5 feet to 25 feet in length. Some were as small as 2 or 3 feet in length. And now we get to more famous astronomers, some that you may have heard of, which the technology started advancing. And we talked about the Galilean telescope and the Keplerian telescope. Well, here they are. Johann Kepler, who was a student of Tycho, and he used his telescope design to figure out the circular orbits. And he came up with this very interesting concept called elliptical orbits, because the epicycles didn't quite make sense to him with the geocentric model. So Kepler started saying, okay, how can we make this work and understand what's actually going on? So he took the idea of the heliocentric model, or the sun-centered model, and started describing elliptical orbits. And he came up with math to support his observations. And he came up with Kepler's laws of planetary motion. And I won't bore you with all the details, but that was one of the largest steps forward with elliptical orbits and understanding how things can appear to slow down in the sky and speed up in the sky, depending on the distance from the sun and the distance from our own Earth. And Galileo Galilei used a very small refracting telescope. So it was 3 inches. That's the size of the objective lens. And he used a small refracting telescope to scientifically prove the heliocentric model. He also looked at sunspots. He found features on the moon, the craters and things that you can see today. And he discovered that Venus has phases very much like our moon, but Jupiter didn't have phases. So that kind of solidified the heliocentric model, because if Venus can have phases like our moon does, and Jupiter doesn't ever have a phase, but he could also just barely make out the moons of Jupiter. And to this day, we call the 4 brightest moons around Jupiter the Galilean moons. And they are Io, Europa, Ganymede, and Callisto. And he named those because he could actually see them in his telescope, which was a huge step forward. He also figured out that the Milky Way was composed of many stars. And so he sort of started making pinhole drawings of what he saw with the Milky Way to try to start to understand what the Milky Way was. Again, imagine a night sky without too many lights shining up in the sky. And he could actually see the Milky Way quite clearly in certain parts of the year. Now we move forward in time a little bit more, and we get to Sir Isaac Newton. And I'm sure most of you have heard of Newton's laws. And it was mathematics that were used to explain observations. And Newton actually developed a new kind of telescope, which was a reflecting telescope. Most of the telescopes up to this point have been refracting, or the long tube telescopes with lenses. So Newton came up with this idea of using a mirror on the back end, which was a little bit easier to make, and then another mirror in the middle to turn the light rays. So the light rays come in through the open end. they reflect off of a big circular or parabolic mirror. They go up to a tiny little mirror and they turn towards your eye. And so there's a drawing of this on the right-hand side of the early Newtonian or telescope developed by Sir Isaac Newton. He also came up with all of the Newton's laws and other things. So now we move on to another famous astronomer, which was Sir William Herschel. He was the king's astronomer to King George II. Very, very famous. He made his own telescopes. Most of the telescopes he made were actually Newtonian telescopes. So he made a lot of reflecting telescopes, because at this point, most of the refracting telescopes were, sort of 3 to 8 inches in diameter. So they're relatively small by telescope size. And after Newton came up with this design of a reflecting telescope, Herschel realized that you could get a very, very large mirror. I mean, absolutely enormous mirror. I think he was making mirrors that were 2 feet, 10 feet. And I think the biggest one was a 24-foot mirror. Didn't work very well because it was very hard to make a nice smooth mirror that was 24 feet across. But he tried, and he was funded by King George. So I'm not going to say he had unlimited funds, but he had a fair amount of funding to pursue this astronomy work that he was doing. He really got into looking at the Milky Way. He discovered the planet Uranus, and he made a lot of great observations and recorded a lot of them. Now, the unsung hero of this was his sister, Caroline Herschel. She actually supported him. She made a lot of the notations. So there were nights where William Herschel would be out at the telescope looking through things, and he would be describing what he saw to his sister, Caroline, who would go into the house where there was a candle burning, and she would record everything that was going on. So she would record his verbal description, and they would put their heads together after and try to make sense of what they were seeing. She also spent a lot of time on the telescope herself. She discovered 8 comets, 14 new nebulae that had not been cataloged. And she spent lots of late nights with her brother, helping him observe and also making her own observations. And she wrote down everything she observed very, very meticulously, very, very well cataloged. So she's kind of an unsung hero. Because he was king's astronomer, he got the Sir. He was inducted into the Order of Knighthood, where Caroline wasn't, because that wasn't, the popular thing during the day. But a lot of Sir William Herschel's success was because of the dedication and the hard work of his sister Caroline. Now we get to the very modern astronomy, which really, really started a great catalog of comet-like objects. Charles Messier. He's in the top left of your screen here. And originally, he was observing from downtown Paris with a refracting telescope, so a 4-inch telescope, relatively small by today's standards. And he had an understudy, sort of like a graduate student, who then became his full-time colleague, who was Pierre Méchain. And Pierre actually cataloged a lot of the things in what is known now as the Messier Catalog of Objects. Now, the interesting thing about this, and the interesting thing that I like about Charles Messier, is that he originally started the catalog because he was only looking for comets. And what you see next to his picture is a picture that I was fortunate enough to take in the backyard of the comet Neowise that we recently had come by and visit us. So that was over the Jemez Mountains of the comet. So Charles and Pierre were specifically trying to catalog comets, and they're both very well known for their catalog of non-comets. So I find that kind of interesting and a little bit ironic that their catalog of objects, which starts with M1 in the bottom right-hand corner, which is the Crab Nebula, Messier 1, or M1 as it's commonly known. And it went to M103, and there are globular clusters, there are galaxies, there are nebulae, there are all sorts of objects in this catalog of objects that are not comets. And it is now expanded. So originally they went out to 103, and then others sort of added other what they call Messier objects. So depending on whether you're a purist, you stay between M1 and M103. But if you're a normal person like me, you go all the way out to M110. And I was very, very lucky to get M109, which is the barred spiral galaxy just above Pierre's picture. That is a barred spiral galaxy that is a very, very long way away. I think it's something on the order of 80 million light years away from us in just outside of Ursa Major. And I could be wrong about the distance, but it's somewhere in that range. And now we get to the modern tools or things that we use nowadays to observe the night sky. So we're building on all of this history. We have fantastic glass. We have amazing mirrors. We have laser precision nowadays. So manufacturers and even people at home, there are quite a number of our own astronomers here in Los Alamos who have and continue to grind their own mirrors and make their own lenses for telescopes. So there's a wealth of knowledge around this town and around this general area for what we can do with our modern tools. But you have binoculars, the simplest thing. Most people have binoculars in their home. They can go out in their backyard and just take some binoculars and look up at the night sky. And if you have not done that here in Los Alamos or the surrounding areas, I very much encourage you to do that, because the visual accuracy and clarity that you can get at our altitude and with the low light pollution that we have is absolutely phenomenal. That's what got me into this hobby to begin with. When I moved here about 5 years ago, I was on the East Coast for most of the time, and I had a lot of light pollution, which I'm going to get to. But when I came here, I noticed one warm summer night, I went outside and I could see the Milky Way clear as I've ever seen it before. And so I started with binoculars, looking up in the night sky. Then you have refractors, which is like this blue piece to the right. That is a refracting telescope, similar to what Galileo or Kepler might have used, only modernized with better glass and much more precise curvatures and focal points and other things. Then you have reflectors, like in the bottom. The bottom picture is a Mead Dobsonian telescope, and I have one very similar that I'm actually going to take to the dark night tomorrow. So I have a 12.5-inch Mead reflecting Dobsonian telescope, which is a Newtonian design, as we talked about. So we're still using Newtonian telescopes and the original ideas from Galileo as well as Kepler to have these modern tools and these modern things. So then we get to very, very complex telescopes, which are what are on the right, and the drawing on the far bottom left are depicting. Those are catadioptrics, or complex telescopes. So they have a combination of lenses and mirrors and reflectors and a very complex optical path, but you can get very good views and very long views with these very complicated telescopes. But it doesn't take that to actually observe the night sky. They tend to be a bit more expensive because they're more precise. But I got my start with some binoculars and then a basic Newtonian telescope, and I've gone from there. So now let's talk a little bit with modern problems, cities and light pollution. So on the right-hand side, you see this picture of the a picture of the night sky as it is seen from space and with all the lines drawn and everything else. But you see the big city centers like Houston and Dallas Fort Worth and all along the East Coast. You can tell why perhaps I never was very interested in the night sky, because I couldn't really see it that much, with the majority of my Marine Corps career being on the East Coast. But if you look where it says New Mexico, the darkness there as compared to the East Coast is absolutely phenomenal. So we have very, very wonderfully dark skies here, and we want to keep it that way. So there are lots of other PEEC talks and different discussions about how we maintain our night skies in an acceptable way without too much light pollution. On the left-hand side, you see a picture from the side of a mountain overlooking Los Angeles, and you see that light dome, which to an astronomer, that light dome is absolutely horrible. It's bothersome because all of that light going up in the sky tends to blur out what you can actually see when you're trying to look at stars, planets, nebulae, galaxies, and other things outside of this. So people who live in large cities have to go very, very, very far away to even observe the night sky properly. And then you get into discussions about sleep rhythms and safety at night, and there's always going to be a debate or a discussion about safety at night versus sleep patterns versus astronomy. And unfortunately, thus far, astronomy is losing that fight. But there are some certified dark sky sites, and I believe our own Valles Caldera just got certified as a dark sky site. So we do still have hope around here. There's also a Bortle scale of light pollution. So it's a scientific way of figuring out what is visible in the night sky. And it goes from 1 to 9, 1 being a perfectly dark night sky, which I'm not sure that even the Valles Caldera is a Bortle 1. I think it's probably a Bortle 2, and a Bortle 9 would be something like the center of Albuquerque. If you went to the very center of Albuquerque and looked up at night, you would probably be in a Bortle 9 light pollution area. So it determines what you can see. It's got a star limiting magnitude, and the vast majority of Los Alamos tends to be in between 3 and 6. So the fringes of Los Alamos, like Barranca Mesa, North Mesa, some other places like that, tend to be 3 or 4, whereas the center of Los Alamos tends to be around a 5 or a 6. Now, what you can view, I mentioned the altitude. Los Alamos being a higher altitude site, there's less humidity, there's less atmosphere between us and what we're trying to observe. So you get much better views of the night sky just because of the altitude. And you also, when you're viewing the night sky, you have to consider the moon, and you have to consider what phase the moon is in and how much light pollution will actually come from the moon. Because believe it or not, during a full moon, you're not going to see really great views of the Milky Way or other types of things near the moon, because it tends to wash them out, similar to light pollution. So you have to watch for those new moon phases, or when the moon is out of sync and it tends to be rising later or very, very early, where you can actually get some good night views, even when the moon is more than half full. And the bottom left is the Andromeda Galaxy, and the bottom right is the Orion Nebula, the great nebula of Orion. And these tend to be more fall type objects where you can really look at them during the fall and get great views. But right now we're coming out of the galaxy season, so you can see the tail end of galaxies early in the night sky, and late in the night sky you tend to see more nebula or nebulae. Now let's talk about the sun real quick. There are various ways to observe the sun, particularly with solar glasses. You never, ever, ever want to look directly in the sun with your bare eyes. And you never, ever want to use a telescope without a solar scope cover or a specialized solar telescope, because not only can it significantly damage your eyes, but it can also burn and melt the optics because you're focusing all of that energy to a very, very small spot. So don't ever do that. If you're going to observe the sun, use solar glasses, use a specially designed scope cover, or use there are different ways. When there's an eclipse, you can use a pinhole box or different things. Just don't ever try to look at the sun with your bare eyes. But if you use a scope cover, which I use, you can actually observe safely, and you can see some of the sunspots, solar flares. You can see some very interesting things if you're doing it safely and properly. You can also observe eclipses. So this was the last solar eclipse that came around Los Alamos, which was a few years ago, and I captured that from my front driveway on North Mesa. And it was kind of early on in my understanding of how to take pictures of the night sky or pictures of the sun, but I did have a solar cover, and I thought it was kind of interesting to capture at least some of the eclipse that we could see here, because we were under a partial eclipse. Now the moon. We just had a very nice lunar eclipse, except for some clouds, which did kind of obscure us a little bit. But the picture here on this slideshow is not from the recent lunar eclipse, but it was from one a few years ago in January. And then I have a picture of the moon there, and then pictures of the planets that I've been fortunate enough to take. They're not the highest quality, but these I took myself. We have Jupiter, Mars, and Saturn, and relatively decent pictures for what I was working with. And most of these were done a few years ago. So I'm hoping this year, as we come into more of the planet season, I'm hoping to be able to get a little bit better pictures and improve the presentation for all of you. Now, deep sky objects is where I really truly enjoy taking photos. On the right-hand side, we have the Dumbbell Nebula. On the left-hand side on top, we have the Bodes Galaxy and Cigar Galaxy. So Bode was an astronomer, relatively recent astronomer that did a lot of great work, discovered a lot of great objects, and this galaxy was one of the ones that he picked out. And these two galaxies are in the same frame because they're actually quite close together, and they are in the constellation Ursa Major. On the bottom left-hand side, we have the Ring Nebula, which is in the constellation Lyra, and it's actually at the bottom end of the constellation Lyra, far away from the prime star Vega. And then we have the double cluster in Perseus in the center here, which are two globular clusters very, very close together. They're very popular deep sky objects. And then on the right-hand side, we have the Pleiades cluster that I started the presentation with from the early 1000 BC timeframe, where they were seeing the same star cluster that we can see today. And I've taken a vast majority of the photos that are in this presentation with the setup that you see on the left, which is my Newtonian reflecting telescope with a dedicated astro camera and a lot of bits and bobbles. And the right-hand side was used in the advertisement. That's my backyard on Barranca Mesa. And that's me setting up for a night of observing and recording data to try to make really cool pictures. And here are some resources and references that you can take a look at: space.com, nasa.gov, astronomy.com, and lots of different references that I use to pull some of these things together. So I hope that was beneficial to all of you. I hope it was entertaining and educational. And at this point, I will turn it back over to Joyce.
Okay, thank you very much, Jeremy, for that talk. I would like you, if you have them, to please type your questions into the chat. Can you hear me? Please let me know if, Jeremy, if you can't hear me.
Yes, I can hear you.
You can hear
Sorry.
me. Okay, that's great. Okay, so let me see if I have anything in the chat. Yeah, Galen, well, Galen sent a message with some details, which I guess let me ask Galen, since I'm receiving the message, is it okay with me with you, Galen, if I read this message to the audience? I don't know if he's, I don't know if I can ask him to unmute. He says, of course. Okay, great. Okay, so he says, great talk, Jeremy. I just want to point out that the 1400 years between Ptolemy and Copernicus were full of challenges to both geocentrism and circular orbits. I'll mention three prominent astronomers who were active between 1000 and 1200 AD: Al-Haytham, Al-Biruni, and Al-Tusi. Those all sound like Arabic names to me, whose work was used and acknowledged by Copernicus. So I think Galen may have a talk on this astronomy in another part of the world that was going on, and Copernicus actually knew about some of that, so he was possibly building on it. So that's very interesting.
Fantastic.
Yeah, thanks for letting me know, Galen. The only other thing I wanted to say about the talk was, while you were talking about the size of Herschel's mirrors, I tried to look that up, and his famous telescope was called the 40-foot telescope, and it's named because of the focal length of the mirror. And the mirror itself was 48 inches or 4 feet in diameter. Okay, so he may have built other sizes of telescopes, but it's called the 40-foot scope, not because it had a 40-foot mirror, but because it had a 4-foot mirror, and it was 40 foot long, the big tube with the focal length. Yeah. Okay.
Thank you
there
for
may
the
be more.
clarification. Yeah.
Sure.
That's fantastic.
Yeah. Okay. Yeah. Are there any other questions or comments? Please type them in the chat. We have some more time. Okay. Here's a question. I don't know if I could even answer this one. In the years of a geocentric model, how much of that was the result of Christian clergy forcing the geocentric model?
That is a fantastic question that I don't have a great answer for. I believe it was fairly prominent from my research that there was a very large push from the church to maintain the geocentric model, thinking that, you know, the earth was made by God and thus had to be the center of everything. But I don't know the details, so I don't want to venture too much farther from that basic research answer. I don't know if Galen or one of our other astronomers might have a better answer. If so, feel free to chime in, because I don't have all the answers. I'm very much an amateur. I enjoy doing this, but don't always have the answers.
Okay, well, while we're waiting for some other possible answers to that question, if you have any more questions, please go ahead and put them in the chat window. I am waiting. Trying to think if I have any more questions for you. I probably have lots. Okay, Galen writes that he agrees that the conservatism of the church weighed heavily in favor of the geocentric model. So I always hear this maybe simplistic story that Galileo was really imprisoned by the church and persecuted because of the geocentric, believing in the heliocentric, proving maybe, as you said, the heliocentric model, right? Providing lots of evidence for the heliocentric model that were showing that the Earth wasn't perfect, a perfect sphere, and, you know, everything is revolving around it, because Jupiter has things revolving around it. So it's also a great place. And as you said, the phases of the planets could show that pretty easily. So.
And to that end, I was actually quite interested. The first time I got to use a telescope to look at Venus, and noticing that it did, the first time I ever looked at Venus, it kind of looked like a quarter moon. So it had this, like, this little sliver. And I thought, before I really studied any of it, I found myself just trying to figure that out. I'm like, I know I'm looking at Venus. Why am I only seeing a little sliver of it? And it really got inside my head, so I can understand how, wow, this is not, this doesn't fall within the accepted norm. So how do you explain it? And obviously I did a little bit more research and said, oh, okay, because it's inside of our orbit, da, 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 da. But just the first time I looked through a telescope trying to understand that was kind of a head scratcher for me.
Interesting.
Yeah.
Yeah, I know Venus, you can easily see the phases, and it is remarkable. And I think when it's in its crescent phase, it's actually bigger because it's closer to the Earth at that point, since it's kind of getting in between us and the sun. So,
Well, and that's when it looks the brightest. I mean, you can see it like usually near sunset, and it's very, very bright. It looks like a bright star until you get a telescope on it, and then you actually see that you're not seeing the whole planet.
yeah, I saw Venus last night, very low in the west, but I don't know what phase it's in. Do you happen to know? Or does anyone
Not off the
happen to
top of
know?
my head right now. I haven't looked at it recently.
Okay. I have a new question. Can you describe the different seasons of astronomy? When you say it's galaxy season or planet season, those aren't terms I was really familiar with. I think galaxy season, at least at the time we're living in the millennia that we've could go through, is in a certain season. But planet season could change over hundreds of years because the planets are kind of moving around. But why don't you explain what you mean by that? Galaxy season.
Yeah,
and
that's a
planet
great
season.
question. So galaxy season, and this may be a little bit more specific to astrophotography. I hear the term a lot in astrophotographer forums, but I think it actually applies to visual astronomy as well, because if you're taking pictures, you can see it, right? So galaxy season tends to be late winter into early spring. So sort of that December to February, March timeframe. And the reason that has to do with when we specifically can see things rising and setting over our ecliptic. So when you look up at the night sky, and you look very, almost straight up, what we call the zenith, then, different times of the year, depending on where the Earth is around the sun, we can see, and the rotation of the Earth, we see different things rising at different times. So right now, the constellation Lyra tends to be, as soon as it gets dark, Lyra is towards the east still, but it's starting to get higher in the sky. And as we go farther into summer, every time it gets dark, you're going to notice that Lyra is a little bit higher in the sky, and a little bit higher and a little bit higher. So you can also observe this pattern if you look towards Polaris. If you look north towards the North Star, Polaris, and most people could recognize the Big Dipper and Cassiopeia, the two opposing constellations on either side of Polaris. And different times of the year, you'll notice that they're in different positions when the sun goes down. And so the galaxy season is just a period of time when the sun sets and you can look out in the night sky, you're going to see more galaxies, specifically in the constellations Virgo, the constellation Leo. Those are some of the most popular spots to look for galaxies. There are, hundreds of thousands, but observable, there are hundreds that you can see in the constellation Virgo and the constellations Leo, Leo Major, Leo Minor. And so you could see so much just in the winter time because we also have longer night skies. Now, nebula season tends to be the beginning of summer into the fall, because again, that's when the sun goes down and you look out. So Lyra and the surrounding constellations, I tend to look north. So I reference the north a lot. That's just where my backyard's oriented. But the nebula start to be very, very observable early in the night sky up till, midnight, when most people want to go to bed, except for us crazy people that are trying to take pictures of things like behind me. So it's just different seasons. So you have galaxy season, late winter, early spring. You have the nebula season kind of coming on the heels of that. And then the Milky Way is the most observable because of where it is in the night sky, usually during the summer into late summer, early fall. So right now, if you go outside about 11 or 12 o'clock and you look to the east, you'll just see that band of the Milky Way. And so it just has to do with where the Earth is in its orbit and where the rotation of the Earth is relative to our greater cluster or Milky Way and everything else. So that's a long answer to a simple question.
Yeah, so what about planet season? When is planet season?
So you can generally see the most observable planets usually in the fall. Late summer, early fall is what I consider planet season. That's when I get the best views of Jupiter, Saturn, Mars, and on some nights during, I believe it's the early fall, you can actually see Mars, Jupiter, Saturn, and even Venus all in the same night sky, and they're sort of spaced out over the night sky. As you look, you'll see one, then the other, then the other. So it's a very interesting time, early fall, to look for the planets, and if you want to get great views, get pictures, that sort of thing.
I think that would vary more from year to year because Mars goes around the Earth, yes, around the sun every couple of years, 1 point something years. Yeah, I've got the geocentric in my head now, and then Jupiter and Saturn have very long, 11 year, and I forget how many years Saturn takes to go around the sun. 30 something 30 years. I have to look it up.
That is true. So it does change.
It will move around a little bit. Yeah.
But because of our speed and our orbit, we tend to see them in the same place more or less, over a decade type time frame.
Right.
And it will change, but yeah.
Yeah, I never really put that together because I've been around for a long time, 60 years, and I always see them moving around. So can't count on that. But
sure.
Yeah. Okay. Any other questions? That was a really interesting question. Thank you. I'm going to wait for another one.
And I just wanted to say, before we get anything else, just thank you all for attending the PEEC talks. And for those of you that are able to donate, thank you for your donations on behalf of PEEC. And, all of this goes towards our community and to making the community better. So as Joyce mentioned, I volunteer with a lot of organizations. And the reason I volunteer is because I care, and keeping this community vibrant, keeping the science going, keeping people interested in learning as a lifelong hobby, not just a school type thing, is very important to me, and I think to most in this community. So thank you all for attending and for keeping PEEC going.
Yeah, thank you. I would like to also mention that there is a dark night for the Pajarito astronomers tomorrow at White Rock Overlook Park, starting around sunset. And a few people will have their telescopes out, so including Jeremy. So if you would like to drop by and come over and bring your binoculars, and the lights will be turned off in the Sparrow soccer field, hopefully. So you should get a really nice view of the night sky, assuming it's clear, and I think the forecast seems pretty good. Smoke may be an issue, we'll see.
We usually have some very knowledgeable astronomers and folks that have been doing this for many, many years who can explain the night sky, possibly give a a quick tour of some of the constellations visible and how to use telescope equipment. So by all means, check us out at the Overlook Park, the Spiro soccer fields, because there's usually anywhere from 3 to 8 or possibly more telescopes out that are available. And most of us are more than happy to share our love of the night sky and our cool instruments.
We do have another question, Jeremy. There's a question about, are there websites to see recent photos of stars and galaxies? What would you recommend? There's probably lots of them.
Yeah, there's lots. My favorite, I don't know about recent, but some of my favorite sites that I go to a lot are space.com. I do go to the NASA Hubble website quite a bit because it's hard to beat the views that the Hubble Space Telescope gets. But from the amateur side, there is a YouTuber called Trevor Jones, and he runs a YouTube channel called Astro Backyard. And he also has a website, astrobackyard.com. There's an Australian, I believe he's Australian, Dylan O'Donnell, who runs a YouTube channel and a website called, I believe it's called Star Stuff. And so those are some of the YouTube channels that I follow to, watch their growing amateur astronomy and their pictures, and they talk through the process of astronomy and astrophotography as well. There's also a website called Messier Objects. It's Messier-Objects, and they describe some of the history and each object, what it is, where it is in the night sky, how to observe it, that sort of thing. So hopefully those are a little bit helpful. And if you join the Pajarito Astronomers Facebook page, you will see some of my astrophotos that I post on there routinely, just because I love the hobby and I like to share it with folks. So the Pajarito Astronomers public open group Facebook page has a fair number, and I'm always taking new pictures and trying to get good images up of objects. So if you want to join that page, we would welcome you into the Pajarito Astronomers.
Okay, thank you. So those are all the questions I have. So thank you again, Jeremy, for sharing with us tonight. I did want to mention that next week, Akana Peck and Chip Keller will be presenting a talk about the solstice and solstice astronomy. So we're coming up on the summer solstice, the longest daylight day of the year. And in July, the PEEC Nature Center is going to start limited programming, live programming in the planetarium. So we'll be doing that a couple of times a month, as well as continuing the Zoom talks at least a couple of times a month. So we're going to have both opportunities this summer. So we'll see how that all works out. Okay, we have someone that wrote thank you. So yeah, that's great. And I thank you as well. All right, so we thank you again for tuning in, and we hope to see you next week for the solstice talk. Okay, good night, everyone.